there's a few important properties of potential energy that you should be fairly familiar with. And these are listed on page 251, right at the section of section 6.10. The first is that the potential energy of two particles depends only on the separation of the particles and not on their actual position. So it's the separation between the two particles that determines the potential energy of that two-particle system. Another thing is that the potential energy has to go to zero as r goes to infinity. In other words, when these particles are far, far away, we've chosen that to be our 0 point for energy. When you have an attractive force, an attractive potential pulling things together, then the potential energy is going to be a negative number. And for a repulsive force, in other words, a force that pushes the two particles apart, then you need to have a positive potential energy. So one thing that'd be really good to know is how to sketch these different potentials, in particular the potential energy versus time. So let's look at an attractive potential energy. So U versus R. Now, gravitational potential energy is a good example, and as we saw, that one looks something like this. So you can kind of think of, if you were to place a ball on this, what would it do? This ball would tend to roll towards the center. So that's kind of a way to figure out, is this an attractive or repulsive force? A ball laying on this curve, if this were an actual physical surface, a ball rolling on that would roll in towards the center. Another thing to look at is the force. So the force here is related to the slope. So we have a large positive value, but notice we have this minus sign right here. So the force is in the negative direction. In other words, the force on the particles at this point is going to be towards one another. Out here, we have a much smaller slope, but we still have a positive slope. So the force, again, is still negative, just a little bit smaller. For a repulsive potential energy, repulsive force, that's going to look something like this. In particular, the electrostatic repulsion between two like charges. And one way to think of this is, imagine that this was an actual real surface. If you were to place a ball on it and give it a flick, what would that ball do? It would roll in and then come right back out. So that's kind of how you can think of this potential energy. Another way to think of it is in terms of the slope. So here we have a large negative slope, but because of this negative sign, we get a positive value. So the force is in the positive r direction, pushing the particles apart. One other thing that you should really pay attention to are the graphs that they show, figures 6.35, 6.37, and 6.38. So these show how the kinetic energy, potential energy, and total energy relate to one another when you graph those on the same graph. Why is the total energy constant in these three graphs? Why does the kinetic energy have the shape that it does? Make sure that you can answer those questions. Those are really key concepts to have in mind.